some good introduction, particularly for young students who I'm sure will take up the research challenge in this field in future. Okay, so I am Amit Ghosal and I'm from IISER Kolkata, Indian Institute of Science Education Research Kolkata. And here is my email address. I have included my email address just in case anybody has any question or any clarification or anything they want to talk to me on the topic of the talk today or last time. I mean, everybody is welcome to drop me a line. I'll be happy to respond. Okay, so the last talk was this, and we started with talking about length scales and then went into condensed matter physics. So today I will not, I will go straight to something more, which is in at the center stage of research. I mean, something which is at the center stage of research, and I will talk about interplay of strong correlation or strong electronic interaction. That's the same thing when people say strong correlation. Strongly correlated electrons is something which is very important area of today's research in condensed matter, and also interplay of that strong correlation with disorder. By disorder, I will subsume within it some, I mean, broadly inhomogeneities and frustration, everything will be considered as disorder. Ideally I should talk about inhomogeneity, that will subsume disorder and frustration. So basically, when both of them are present together, then what happens to their effect in physical system, in condensed matter system? So this is an outstanding challenge in condensed matter physics. It's an outstanding problem in the sense that if you think of non-interacting free and clean system, free means free of any interaction or free of strong correlation or free of any correlation, and clean system means that it is not disorder. Disorder is essentially impurity, so it's a pure system. So the knowledge of condensed matter physics or physics by and large, which is developed over the whole 19th century, is the one where we assume a system to be like this to begin with. I mean, that's always a fair assumption, and all our knowledge of metal and insulator and so on and so forth, I mean, everything that we learn in the first course of condensed matter physics in colleges and universities, I mean, that basically deals with free and clean system, pristine system, if you want to if you want to describe it that way. And also we know how to deal with weak interaction and weak disorder. I mean, both being weak, I mean, either one of them is weak and the other is not present, or both of them are present, both are weak, it is fine. Essentially, whenever it is, I mean, either interaction or disorder is in the perturbative regime, meaning that's the energy scale. When you add disorder or electronic interaction, that energy scale is smaller than other relevant energy scale. So these are very standard jargon like statements, but it is basically what it means, that we can somehow use them perturbatively. Whenever we can use either disorder or interaction or both perturbatively over a free and clean system, we know how to handle systems, essentially, how to handle physics of some material. So that knowledge has been developed over a long time. However, the interest for today, I mean, I would say that that's the area of interest for last couple of decades in the past, as well as it will continue for some time in future, is go beyond this perturbative regime. So that's what we are interested in by and large. So enormous progress has been made in the experimental front. I mean, when both are present and sizable, I mean, both are not so small, not in the perturbative regime, and experiments are there. Experiments have gone too far, I would say. I mean, really, I mean, we are in a position where our experimental colleague can fabricate very perfect material with strong correlation, and they can also have a controlled way of introducing disorder or inhomogeneity in the system. So that's fantastic. So that puts pressure on us meaning theorist. I mean, I do theoretical study. So to understand or to comprehend the experimental finding, accuracy and control or tunability over measurement have also gone up, which aided the research of the interplay of these two objects listed here. So I work in that area, and I work using computers. I mean, computational growth had actually helped the research in this direction enormously. And I will pick up two problems for discussing today, in which broadly falls in this category. And I will give you an idea. First of all, I am a phenomenologist, in the sense that I want to understand a phenomena, and for that, for understanding that phenomena, I would like to develop various calculational tool. So it could be analytical tool, it could be computational tool. I prefer to work with computational tools, and that's my area of research. So I will pick up computation. I'll talk about two problems and two computational tools. So I will talk about two problems in which effective electronic interactions, in one case which is negative, I mean, negative meaning attractive interaction, in presence of disorder environment. And I will talk about a second problem where the effective, or where the bare electronic interaction which is repulsive. I mean, bare electronic interaction is always repulsive. How it can become attractive is already interesting question, and I'll address that very quickly. So there are many examples. Sorry about this black patch. I mean, so it will go away. So there are many interesting examples which are areas of present research. I mean, two-dimensional metal insulated transition, 2D MIT is how I have written it. And then superconductor insulated transition, HTSC stands for high temperature superconductor, MBL, many body localization. And then there are spin liquids. I mean, these are all examples where both interactions and disorder or inhomogeneity, they compete or collaborate to realize interesting physical effects. So we are going to focus two such examples. Okay. So for the first problem, I'll talk about inhomogeneous superconductivity. So let's see what they are. So first, I mean, to begin with, anything to do with superconductivity must start from BCS superconductivity, because that's something we have a very well understanding of. So this is something that Bardeen, Cooper, Schrieffer, which is abbreviated as BCS, Bardeen, Cooper, and Schrieffer, have given a theory which explains beautifully the superconductivity that we realize in experiment in metallic superconductors. So BCS superconductivity is a very good description for all metallic superconductors, which means that if you take any metallic element, and you cool the element to a very low temperature, it goes superconducting. So superconductivity, as you know, it's something that I was mentioning last time during last lecture. So it's a conductivity which is super, in the sense that so conductivity does not come with any loss of current. I mean, so if you pass a current through a superconducting wire, so there will be no resistance. Resistance will be literally zero. So you will have a lossless flow of current. So of course the whole subject became alive early days. I mean, in late 50s, because of the possibility of the industrial use of this superconductor for lossless flow of current through circuits. So how does superconductivity work? I mean, that itself is a detailed subject, and I don't want to go details into that, but I will for my purpose I will tell you something which is very simple. So first of all, so the clean BCS superconductor, so BCS theory describes only clean system, I mean no disorder. So here, as you see, there is a phase diagram like the one I was motivating last time. The phase diagram here is as a function of temperature. So there is a temperature axis, there is a disorder axis. So this is where I would like to go to. But then for this introduction, I'll not worry about this plate disorder versus there is some superconducting correlation scale. So this is superconducting correlation. So I'll tell you in a moment. So for example, if we focus on this particular plane, so plane of the paper or plane of the slide, if I consider, which is this light blue surface that I have shown here, this surface. So here on this y-axis here, I am plotting superfluid density. So superfluid density measures a superconducting correlation. It's a transport property that it's a response function. I mean, that's the best way to say that. But simply speaking, superfluid density is something which tells how much of superconductivity does really exist in the system, in the sense that it will go to a largest value, which is often normalized as 1. It will start from 1, where the system is fully superconducting, and as you increase temperature, so superconductivity is a low temperature phase, just like ferromagnet and so on and so forth. So at low temperature, the system orders and becomes superconductor, and superfluid density goes down as you go up in temperature and disappears at some critical temperature, which is called TC, superconducting critical temperature. So what is very interesting is that also there is another quantity which is an identifier along with superfluid density. Actually, there are several measures which will identify the superconducting state. So one of them, of course, is superfluid density. The other one is an energy gap. So it turns out that the ground state of the system, I mean the lowest energy state of the system, and there is a gap in superconducting state. I mean, so the first excited state will have an energy gap from the ground state when it is a superconductor. So as you increase the temperature, the energy gap also depletes and again disappears exactly at the same TC where the superfluid density disappears. So beyond this, the gap goes away and the system becomes a metal. So this system at high temperature becomes a metal. So and then there are other interesting properties also. So it is probably fair to mention at this point of time that this energy gap is actually, it turns out, I mean, it need not be for any general phase transition the way we are discussing last time, but in this particular case, the energy gap is same as the order parameter. So in BCS theory, clean BCS superconductors, the order parameter which talks about a ordered state of superconductivity is identical to the energy gap. In general, this need not be for any general system. If there is an energy gap, that need not be the order parameter. So it just turns out to be same in superconductor. Okay, so now how superconductivity arises in the system is something which is described by BCS theory of superconductivity, and I'll not go into that. But one of the key ingredient in that is that the electrons, which are the charge carriers of a superconductor, instead of repelling each other in a superconductor, they attract. And that's already very exciting thing, because it's not something which is common, right? I mean, we know that electrons are like charges, so they must repel each other following Coulomb repulsion law. However, in superconductor, they attract, but they are no more the electrons, bare electrons. So you can say in different ways. We can talk about some effective particles which are like electron but not necessarily electrons. The effective charge carrier object, they start attracting each other. Or you can say that actually electrons do attract each other, but it is not a direct attraction. I mean, direct interaction is still repulsive, but it is an effective attraction. So that's actually more of a common. That's a better picture. So what happens is pictorially defined here, and I'll quickly take you over it. So let's start from one cycle of this picture. So here, what is being done is, let's say this is a crystal. I mean, this periodic array of atoms in the system. So these are positively charged ions or atoms, which makes the crystal of a system. So at high temperature, which is this, they just vibrate. So now if you cool down this temperature of this object, go to a very low temperature, then what happens? They become, their vibration stops. I mean, not really stops. Their vibration becomes weak, and then what happens is, as you can see, I'll now show you that there is a red ball here. So that is like an electron. So when the electron moves through the crystal, you can see that every time as you follow the electron, so this positive charge blue dots, they are getting attracted towards electron. So, which is obviously true because electron is negative charge and these are positively charged objects. So what happens is then near the electron, wherever it is, there is as if an effective higher density of positive charge, right? Because as you can follow that the positive charge blue dots are coming close to electrons, so the density suddenly increases surrounding the electron. So that is what happens in the system. Now, because that happens, and now you can see it here. So it is a bigger picture that one electron, let's say there is a there are two red electrons, as you can see. And you see that when the first electron moves, these lattice points get closer to it, which are positively charged ions. So as a result, there is a second electron which will get attracted to this electron, not because of the presence of the electron, but because these positive charges have come closer to that electron. So the first electron has passed by. I mean, it has gone far, but then this larger ions or atoms, ions in this case, which are there, positively charged objects, they move very slow. So if they get attracted, they will take some time to backtrack to their equilibrium position. Until that happens, a second electron get attracted towards this excess positive charge density. So it will appear then as if a second electron is actually following the first electron. So it will give an impression that the second electron is being attracted by the first electron. So it's an effective attraction. I mean, it is certainly not a direct attraction between one electron and another. It is the one electron which is disturbing the positive charge density surrounding it, or rather increasing the positive charge density surrounding it, which attracts the second electron towards it. So that's the kind of effective attraction that we are talking about, and that's essential for superconductivity. At least that is essential for BCS superconductivity. So this is often referred to as phonon mediated interelectronic attraction. Effective attraction. Phonon is what is known as the vibration of this lattice, because of which these positive charged objects are getting closer to the electron, and it is that. So you can think of it. It is that electron phonon interaction to which another electron is getting attracted. So it's it is a phonon. It is called phonon mediated electron attraction. So that binds up two electrons. They make up something which is called a Cooper pair. And so Cooper pair, I mean, you can loosely think of it. I mean, it's not exact analogy, but it is a good analogy, I would say. So the way you should think of superconducting transition, I mean, the way a system goes superconducting, is that these were all electron in the metallic phase. Metal, as we spoke last time, can be thought as a electron gas. So it was like individual electron. Now, once the two electron gets paired up, they're called Cooper pair. So they start behaving like a bosonic object. There are different ways of showing that this is a bosonic object. Let's not get into that details, but they will act like a boson. And once they start acting like a boson, as you have heard about it, I mean, that there is something called a Bose-Einstein condensation. I mean, if you have a system of boson at very low temperature, they can condense into some condensate or condensate phase. So superconductivity is, roughly speaking, something very similar to that. I mean, once the electrons pair up, they form boson. And because electrons and bosons are very different objects, so once they form bosons, then the system should show properties which are very different from electronic system like a metal. So that's what superconductivity is, broadly speaking. All right. So superconductivity is identified. Sorry, I'll put my cursor away just so that we can see what is written there. So it says that superconductivity is a quantum phenomena, and it is identified by some order parameter which is referred to as delta. And it's a complex order parameter. I mean, delta is a complex number. It has I mean, one can show that it has to be a complex number, and which means that it has an amplitude and a phase. So it turns out that for simple BCS superconductor, the phases are all locked. I mean, basically, you have for every site in a system, you can define delta or whatever that be the order parameter. I mean, that's a local object. You can define it at every point in space, the delta. And however, I mean, while delta and hence delta and theta, delta mod, which is the amplitude of order parameter, and then theta, which is the phase of order parameter, they are local object. However, it turns out that all theta point to the same direction in a BCS superconductor. We'll say more about this amplitude and the phase of the order parameter. And it is the same order parameter which goes as an energy gap, as I say. Okay, so now once we learned about what is the basic superconductivity. I mean, we at least have an idea of what is the basic superconductivity. I'm so sorry, this should have been here. Let's learn a little bit about disorder and localization. So what is the effect of disorder? Forget about even superconductor. Just in a regular metal, what happens when you put disorder? So before even going there, so disorders are like impurities, but what exactly is disorder? So for theoretical modeling, and of course theoretical modeling makes sense because it's sort of consistent with the experiment, the way you can describe disorder is that disorder is some random potential energy that you stick to every lattice point. So you can think these blue balls forming a lattice, a square lattice, just for simplicity in a system. Just think about these blue balls. Okay, so this is like a square lattice. So now what you now do, I mean, so just blue balls as a square lattice would have no disorder. Now what I do, I attach some kind of potential to each of these blue balls, meaning each of the lattice point where electrons can stay or can come and sit in a lattice. So this potential well that you have, I mean, this is a potential well, which is the attractive. I mean, that's why it is negative. I mean, just the way you do quantum mechanics problem potential well, like that. I mean, with a very narrow width, essentially. And then in some cases, you will have a hill. I mean, this is not a well, but potential hill. So every site will have either a potential well or a potential hill, and their magnitudes are all random within a limit. So that's a very nice theoretical description of disorder, and is quite consistent with certain experiments. So basically, we're saying that by disorder, what you mean is, I mean, this is a non-magnetic disorder. So that requires a little more clarification. I will probably tell, but essentially, you can think these are like potential disorder. Every lattice site has either a potential hill or a potential well. And now the strength of this potential can be chosen from some distribution. So in this case, for simplicity, I choose it from a distribution which is called a box distribution because it looks like a box. I mean, P of V is the strength of the well, and that remains between minus V to V. I mean, so the height, I mean, this is a positive one, so this height cannot be larger than V, and it cannot be smaller than, I mean, the well cannot be deeper than minus V. So these are the two bounds. And then within this range, any value is equally likely. That's the meaning of the box. I mean, that's the distribution. That's the meaning of this distribution. So now, if I put this thing as a in a two-dimensional plot, let's say that the blacks are like the negative points, like the wells here, and whites are the white points at the potential hill. I mean, this is objects like this, whites are hill, and they're random. So there is no correlation between one site to the value of this potential between one site and another site. So so then it is clear that because blacks are the one which is potential well, so these are the regions which is black dominated, I mean deep well, and these are the regions which is white dominated, that's high hill. So and then they're equally likely, any value is as probable in the system as any other value. So that's the meaning of this flat top. So it need not be the case. I mean, depending on your physical problem, you have different shape of the this distribution, probability distribution of this disorder potential here. So that's the description of disorder in a system, in a simple-minded manner. So what has been found that even if you are not talking about superconductivity, no interaction, just free electron in a disordered environment, disorder has many interesting effects. For example, electron wave functions can be either extended. I mean, in clean system, if you have a one-dimensional system, the free electron gas will have a wave function which is a plane wave. So when you don't have really a completely free electron gas but little bit of disorder, you still have a wave like a plane wave, but some kind of a random plane wave. I mean, but then the main point is here is that you, at least for small disorder, small v is the disorder strength as I have described. So at small disorder, you will still have an extended state. That means this wavy nature will persist from one end of the system all the way up to the other end of the system, right? However, it turns out when you have disorder which is very strong, so then the wave function actually get localized. By localized, what I mean is something like this, that there is still a wavy nature, but this wave is a highly damped beyond a distance from some particular region. So here, so you will say that the wave function is localized as this at this particular region of space, with a length scale which is like this. Let's say this falls off as exponential. In fact, it falls off as exponential in real system. The wave function falls off far away from the point where it is localized as exponential minus CR. I mean, which is given here. So it gets localized. So what it means that within a system, so let's say if you have a system, so of course if it was extended and if I was to plot the wave function was persist for the whole system. So this is the system where there is a disorder point, and if the disorder value was weak, then the wave function will have value everywhere in the system. I mean, it will have modulation from one end of the system to the other. On the other hand, if the disorder is strong, so what turns out that the wave function get localized in a small region. So here black means the opposite. Here black means that the wave function is large. The component of wave function is large. So it is large only in a small region, and that region is of the scale of psi, which is called a localization length. So a function follows this. Follows a form like this. So it becomes localized. So now you can easily imagine that when your wave function gets localized, then the system becomes an insulator, right? Because if the wave function becomes localized, means that electron can stay only within this limited region of space. So there is no electron to carry current from one end and go to the other end, because electrons have got locked in a small region of space. I mean, it is not there everywhere. So a transition from, by increasing disorder, a transition from extended wave function to a localized wave function is actually a transition from a metal to an insulator, because here wave function extend from one end to the system to the other. So electron can conduct and the system could be metal, but in the other extreme limit of large disorder, it becomes insulated. Okay, so now there is something very interesting theorem. I mean, no, not theorem. I mean, this is actually a result. I mean, it's not called theorem. Very, very powerful statement that at least for non-interacting electronic system, in the presence of disorder, for dimension less than equals to 2, all wave functions are localized. So basically, so there are many states of the system which are wave function. So all the states become localized for any arbitrary small value of disorder. So that's very interesting. That would mean that for dimension 2 or less than 2, dimension 1, there cannot be a metal. Because if there was a metal or forget about even metal. Sorry, I mean there is no metal. So if there is no metal, there cannot be even a superconductor, right? I mean, naively thinking, because superconductor is a conductor which is super. So if you cannot even have a conductor, if you have an insulator, how can you have superconductor? So that's the question people asked in the early days. And so that's the kind of question people have asked. And early in the game, I mean, when people started looking into superconductivity, more or less at the same time when BCS theory came up, I might be wrong with this year. I mean, it may be 1959. Please check. So Philip Anderson, who is one of the champions of condensed matter physics, I mean, who has enormous contribution to condensed matter physics, he came up with a very powerful conclusion in terms of very simple arguments that as long as the system remains fairly large, no amount of scattering, which means no amount of disorder, because I'm quoting the statement from Anderson's paper, that no amount of disorder which leaves the substance a metal. I mean, there's a very important statement. So which means that you are always talking about not very strong disorder. I mean, even though you're talking about scattering from disorder, you are not talking about a very strong disorder, but the statement is that would be capable of actually destroying superconductivity. So essentially, Anderson's statement is that at least when the disorder is not extremely large, disorder cannot destroy superconductivity. So that itself is very interesting, because just now we said that in 2 dimension at least, disorder actually kills the conductivity altogether. At least at zero temperature, at very low temperature, there cannot be a conductivity because the system will remain insulated. Of course, it is a statement with non-interacting electrons, and superconductivity requires interaction. But the statement here is very interesting, that superconductivity doesn't get destroyed by disorder. Right? Even conductivity gets destroyed by disorder, but superconductivity doesn't. So this actually raised a lot of interest in this subject. I mean, what will happen to the superconductivity in presence of disorder? Okay, so now if you, so this is what I said. So what will happen, as you can imagine, we said that this delta, which is the order parameter of a superconductor, which has an amplitude and a phase part, and these are local. So in clean superconductor, because it's a translationally invariant system, I mean, these objects, I mean, theta and delta will have a uniform value across the system. But in disorder, they will not, right? So there it will start fluctuating in space, because these numbers delta and theta, delta mod and theta, they will be site dependent or space location dependent in the system, depending on the local environment of disorder. And thus impurities will cause spatial fluctuation. Can that destroy superconductivity? So that's the question people have asked for a long time. And this is, I didn't put the year, but put the other credentials to find the year. I think this was an experiment in early 90s, where what one is showing that even though there is Anderson theorem, what one is taking is a bismuth film, which is a metallic film, which goes superconducting. I mean, there is a very faint traces that the conductive. I mean, this is a resistivity or seat resistance per unit square. So that is coming down, remaining uniform. I mean, remaining unchanged, and then suddenly here it goes superconducting. So this is a superconducting transition temperature at some low temperature, low value of temperature. Now, there are many different superconducting films. I mean, each being given by a particular trace here. Each film has a trace, and these films are identified such that as you go from here to the upper curves, the disorder increases. And what you see is that not only as you go increase disorder from here to here, the superconducting transition temperature goes down, and it goes further down with even more disorder, goes down even more with increasing disorder. Not only it goes down, march towards zero, the superconducting transition temperature marches to zero. Beyond the critical disorder, it doesn't remain superconductor. So you probably know that you identify metal as something where if you lower the temperature, the resistivity, or this is a two-dimensional film, I said. So in two dimensions, resistance and resistivity are the same thing. So the resistance or resistivity will, I mean, for superconductor, it will disappear. Resistance will go to zero, and hence so high and super conductivity. For a metal, this will go hit this y-axis at a finite value, finite intercept. That defines metal in the limit of zero temperature. On the other hand, its insulator, if by lowering temperature, the resistance starts going up. So basically, the lower in temperature you go, the system becomes less and less conducting, or the resistance becomes higher and higher, and actually diverges in the limit of zero temperature. So it seems that there is not only that a superconductivity gets depleted, I mean, not only superconductivity gets destroyed, you can actually go to an insulator, straight from superconductor to an insulator by tuning disorder, because you are actually increasing disorder going from here to here. Okay, so this has been found. So this will appear that this is apparently contradicting the Anderson theorem. Actually, indeed that is true. I mean, that's not untrue. However, one has to keep in mind that Anderson theorem is saved because it says that I mean, as long as the impurity is such that which leaves the substance as a metal. So I mean, because the substance is not metal here at all, it is insulating. So that's why Anderson theorem will not apply. But this just says that Anderson theorem just doesn't apply. So can one develop a good understanding or description for a physics like this, where by introducing disorder, the system can go from a superconductor to something like an insulator? And this field, I mean, understanding such transition, not just for a regular BCS type superconductor, but in broad variety of different kind of superconductors, actually gave rise to the whole area of study, which is called superconductor insulated transition. Okay, so that is basically some basic piece of phenomenology for this for the problem, for which I would like to quickly develop some kind of tools, computational tool, and I will quickly describe that to you. Okay, so now please bear with me. I mean, please, because this now I'm going to show you two slides with lot of equations written there. It is not that we are going to be interested in all of that, and probably we will be interested in very few, but to give you an impression of how do you run the technology, we need to show a few equation, and I'll try to keep this description as brief as possible, and then I'll get back to something where I can physically motivate you about the thing we are interested in. Okay, so for clean system in a as a BCS superconductor, so what describes a BCS superconductor fairly well is an attractive Hubbard model, so which is written here. So I won't I mean, so here there is a VI which is disordered just the way, I mean, here I is a lattice site. So VI, I will suppress VI to be zero for all values of I. So everywhere I will suppress V to zero when I describe a clean system. And that's what we are trying to do here. So if you take an attractive Hubbard model of disorder, Hubbard model without disorder, just Hubbard model. So what this equation means, that this first term talks about electron hopping from one side to the nearest neighboring side. So like there is a hopping amplitude T by which an electron, which is with spin up in this case, red one, I mean like an arrow up. So I'll call that electron with spin up, that hops from here to this one, and it can hop actually to anywhere, but for simplicity we are considering a model where the hopping is allowed only from one side to its nearest neighbor. And in two-dimensional system, as you can see, there are only four nearest neighbor. Like this is a nearest neighbor of this guy, this is the other, this is one, and this is one. Right. So the hopping is possible only to those sides. So this is a caricature of a kinetic energy, because kinetic energy means the energy which tries to move an object in space from one side to other. So this is just that. Only restriction is that it moves only to a limited distance. But this is the essential job of kinetic energy. Now the second term, which is an interaction. So what it says that there is an attractive interaction because it comes with a negative sign, which is U here. When two electrons, sit on the same side I, there is an attraction U. So that's all we have to care about. And then there is a mu term, which is just to say that one is working with a grand canonical ensemble. That is what it is called in statistical mechanics. You might have read about it. We basically talk about H minus mu n, and that's what it is doing. There is a reason to work with grand canonical picture, grand canonical ensemble when you try to describe superconductivity, but that's a matter of technical details. So now these electrons are described by what are called electronic creation and annihilation operator. The one with dagger is a creation operator and one without dagger is an annihilation operator. They follow fermionic anti-commutation rule. That's the signature that these particles are fermionic, or electron. Electron is a fermion, right? So if you start with this model, and you do some simple massaging of the Hamiltonian in the form of going to a momentum space, and also pick up the particular contribution, particular momentum state contribution, which will maximize the pairing attraction, because that pairing attraction is this U term. So then you land up with what is called a reduced BCS Hamiltonian, which is given like this. So this is the energy spectrum, which comes from the kinetic energy part. It is written in momentum space, where you can diagonalize this Hamiltonian, the non-interacting Hamiltonian, and the interaction is given like that. This is just a limited possibility of all possible ways you can write down this interaction, which is given here, but that has some additional physics of BCS, and I'm not describing this, mostly to do with this kind of picture that we talked about, and also maximizing or constructing energetically most favorable situation for superconductivity. So that leads to this reduced BCS Hamiltonian, which upon mean field decomposition, you create some BCS mean field Hamiltonian like this. So that's something what people work with. So we will do something similar. Only difference is that what we have done here, we worked, as you can see in BCS theory, one works in momentum space. And that's natural, because you want to talk about spatially homogeneous system or translationally invariant system. So if there is a translation symmetry, you know that momentum is a generator of translation. So momentum is conserved, and it is easy to work with momentum space. You gain a rather high computational advantage by going to momentum space. That's what we do all the time. On the other hand, if you are working in with disorder breaks translational invariance, as you know, because we just talked about this disorder here. So as you see, there is no translational symmetry between one side to the other, because all disorder potentials are random. So in this case, we have to develop the same kind of a theory like BCS theory. However, it has to be constructed in the real space. So such thing was first done by Dejenes. Dejenes is the person who have implemented that. But then Bogolubov was the person who first derived some transformation from electron to some other fermionic object like gamma here, which diagonalizes the BCS Hamiltonian. So that's what Bogolubov did. This Hamiltonian can be diagonalized using Bogolubov transformation. Bogolubov developed that for clean system, which will work in momentum space. Dejenes modified it for working in real space. And then you can treat disorder. That's the point. Only price, or a huge price that you pay for that, is that you have to construct. In BCS theory, if you have to develop this calculation in momentum space, you will have to deal with diagonalization of just 2 cross 2 matrices. On the other hand, when you have to do the Bogoliubov-Dijen's calculation, then then each of these are like n cross n matrices. So you have to work with a 2n cross 2n matrices, where n is the number of site. So if you have a large system, let's say some 100 cross 100 system, so you will have 10 power 4 times 10 power 4 matrix. So if you have to diagonalize that matrix, that's not a very trivial job. So the way the mean field calculation or Bogoliubov calculation goes is that you start with the mean field Hamiltonian, where you have something which are like order parameter, which is site dependent order parameter, whose values you don't know to begin with. So that is like delta. You will also have to work with mu. Mu becomes mu I because of disorder. Effective chemical potential picks up a site dependence in some particular way, as written here. Mu I is not just mu, but something to do with the local density, and also there is local density, which is the other order parameter. So all these objects go into the Hamiltonian, though you don't know their value. So a Bogoliubov-Dijen's calculation amounts to the following: that you start with a guess value of this order parameter which enters in your Hamiltonian, construct the Hamiltonian, diagonalize the Hamiltonian, because once you have constructed the Hamiltonian in terms of some guess values of this object, you can construct the you can diagonalize the Hamiltonian. And the point is that if you have diagonalized the Hamiltonian, even though you have used mean field theory, which is an approximation, but let's take that to be a very good approximation. In fact, BCS theory is a mean field theory and is a fantastic approximation. So let's say it is nearly exact. So even if it is exact, and if you have diagonalized the Hamiltonian, then you should be able to recalculate, or you should be able to calculate anything under the sun. And by that token, you can calculate all these objects like delta using the eigenvalue and eigenvector, delta, this local density, and mu. So start with some guess value in the Hamiltonian, diagonalize it, and recalculate them using the eigenvalue and eigenvector. And then what you will find is that the recalculated value of these objects are not same as the one that you started with, because it will be same if your guess was exactly the solution, and which never happens, right? So the whole job is then to iterate the process such that whatever guess value you put in the Hamiltonian, inside the Hamiltonian, and then diagonalize and recalculate. So input and output values of these objects, the self-consistent parameters of the calculation, they become identical. The one that goes in the input. So once that happens, you will say that the self-consistency is achieved. So this is the method of Bogoliubov-Dijen's calculation. So now there is a recent book. Recent meaning it is still out for last. It is existing for 2-3 years for sure. Maybe 2016 or 17 it came out. So this is a book on Bogoliubov-Dijen's method and its application. So that's what I am discussing here. So you can make it a little more general, call that an inhomogeneous mean field theory, which is not just Bogoliubov theory, but you will talk about Hartree, Fogg, Bogoliubov, all channels of mean field theory. Again, that's a technical jargon. So now I give you the flow chart of a Bogoliubov-Dijen's computer program, which is that you make a guess. I just said that you make a guess of this object, and then you diagonalize the Hamiltonian using the diagonalization, using the eigen system, that is eigenvalues and eigenvectors. So you recalculate the object with which you started your calculation, and then ask whether within tolerance, whether this recalculation which is the new delta, is same as old delta. Delta is just one of the order parameters, and that too it is for all sites that you have to calculate. This is just one such site. If this is true for all sites, if the difference between them is less than some tolerance, which is some very small number like 10 power 6, 10 power minus 6 and 10 power minus 10, you choose your tolerance. So if all the self-consistent objects are actually self-consistent, if they are not, if they are, then this is very good. You just come out and then record the delta and rho, record all the self-consistent parameters, and then you end the program. If not, Then you go back and reconstruct a new case for delta and rho, just to put it back here, and you iterate. And any iterative procedure is best done on computer, and that is exactly what we are going to do. So there are two parts. One is this iteration, which you want to automate, and hence you put it on computer. And also, second thing is, you will have to diagonalize a very large matrix with where you want to record all eigenvalues and all eigenvectors. I mean, which is not so trivial. I mean, it is easy to find an eigensystem. I mean, easy to find the lowest eigenvalue and the lowest eigenvector, or lowest or highest. I mean, some few eigenvalue and eigenvector. They are very powerful numerical technique for that. But when you need all eigenvalue and eigenvector, then you still have to do it numerically, and to go to a large system, you have to use various numerical tricks. So that's the part which requires you have to flex numerical muscles. And even more importantly, you have to flex numerical muscles to reconstruct a good value, good guess for the next iteration. Because so the expectation is that maybe you will not have a very good guess to begin with, but you will improve the guess in every process. So that has many different algorithms, and that people have researched on, so such that you can do it, and you can do pretty well. And once you do pretty well, then in the end you have a self-consistent value of all order parameters, and that means that you have diagonalized the Hamiltonian with the appropriate value, and that leads to, and then you are ready to calculate and interpret physics to your heart's content, essentially. So there are many things which I've learned. So now I am not going to discuss all of it, because this is too much of many things people have discovered. I mean, we have done many important calculation in this area long time ago. So there are some of the early papers. I mean, sorry about this black patch, it is there. But some of the physical result, let me tell you, that what turns out, that because this delta, I mean, this delta is the amplitude of the order parameter only. I mean, this is the mod of delta, essentially, what I'm plotting. So that for weak disorder, I mean, so for zero disorder, it will be all uniform across the system. That it must be. With disorder, it becomes for it develops some inhomogeneity, and then inhomogeneity increases as you go to larger and large disorder. And in the largest disorder, you end up with a system which breaks down into smaller pieces. So it is like you develop some island. So the way it happens is that these are then called, we call superconducting islands. So system becomes, so first of all, disorder is completely random, but it seems that these regions of large local delta region, or regions of large delta, actually they conglomerate. I mean, they make puddles, they make blobs, and such blobs are, I mean, as I circled it in certain cases, so they are called superconducting islands. It's not that the value, wherever there is some delta, even at large disorder, they are randomly scattered everywhere. In fact, there are many earlier theories of disordered superconductivity where people assumed that these are randomly scattered everywhere in the system. On the other hand, we actually developed this through this calculation, and then because of this conglomeration of regions of large delta, which are separated by regions of very small delta or non-superconducting regions, the the nature of transport changes very, very significantly than having I mean, some scattered points randomly all over the space for delta. For example, it turns out that the superfluid density, I mean, in this case, it is not plotted as superfluid density. It's called the order parameter, but let's off-diagonal long-range order. So that's another superconducting correlation like superfluid density. So there's certain superconducting correlation that decreases monotonically with disorder, whereas energy gap, which is this other one, that it decreases somewhat but remains finite. In fact, it starts increasing. So these two objects, while behave exactly in the identical manner for low disorder or zero disorder in BCS theory, at large disorder they separate out, and this has very important significance for the behavior of superconductor. Then there are many other things. Superfluid density actually goes down monotonically, and one can show that once you create a superconducting island like this, just the way I just showed you, I mean, in a calculation, I mean, in a microscopic calculation, once we derive that, what one can show that phase fluctuation can take advantage of this disconnected superconducting islands and kill the superconductivity, in the sense that in a way where the I mean, the fact of phase being rotating, I mean, so phases, as I said earlier, that phases are all locked or all same value in a BCS theory. So within superconducting island, they will behave like all being in the pointing to one direction phase of the system. On the other hand, when they are islands, then phase can rotate a lot in regions where there is no superconducting island. That's the main point I'm trying to say. As a result, this superconducting island doesn't speak to this superconducting island, doesn't speak in the sense that there is no correlation of the phase between these two islands, and that has a very important role of destroying superconductivity. So, for example, this aspect was not included in Anderson's theorem, because there it is assumed that the system remains metal. So the region in between is actually not metal, it is insulating. So because the system breaks down into like metallic pieces which go superconducting, there is a provision for superconductivity to deplete rather rapidly, which is not included in Anderson's theorem or Anderson's description. So these are again the evolution of inhomogeneity. So it's just interesting to see that the previous picture I showed, these are actually from long time back. These are 2001 to, I mean, around that time when I was working on this problem for my PhD, and then these are more recent times. The content of the figure is same as what it is here, that evolution of inhomogeneity, and then causing forming superconducting islands like this, separated by regions which is dark blue, so which was plotted here as I mean, white regions. So it's just that the technology changes, and then you produce little more nicer looking picture. But beyond that, there is not too much different in the actual phenomena. So now this idea can be taken forward, and one can look at various things, and we kept looking into various different aspects. I mean, disorder in high temperature superconductor, vortex lattice in high temperature, clean high temperature superconductor. Vortex lattice is something what you form by application of a external orbital magnetic. Let's just talk about magnetic field by application of a magnetic field in the superconductor. And vortices, as you if you are there in my last talk, you know that this is some kind of an excitation, I mean, which is topological in nature. We talked about it. So that those are found in superconductor also. So that's something that we have studied. And we talked about ferromagnetism in unconventional superconductor in an earlier publication. Then we talked about competing order in unconventional superconductor, vortices in disordered superconductor, some FFLO state. So something which there is a exotic superconducting phase called FFLO, which is found in presence of a Zeeman field. So here I said vortex in presence of an orbital magnetic field, but it is the Zeeman coupling which the magnetic field couples to electron spin. So then you have an exotic phase of superconductor called FFLO. And then we have been talking about strong correlation in strongly disordered superconductor. This is like the AGN where I am interested to venture. So this is exactly far beyond the perturbative regime, where we are talking about strong correlation and strong disorder simultaneously. So everything is development over the simple Bogoliubov-de technique that I have outlined. So once you master one technique, the possibilities are essentially endless. You can do more and more stuff. Some of it I have given here. And much of our work have found experimental verification. So that's very, very reassuring that we are doing nice things. In terms of uncovering the inhomogeneities and their evolution. All these results are from the group of Pratap Raichaudhuri from TIFR Mumbai. We have collaborated with Pratap and his team. And much of the physics that because of the lack of time, I'll not spend time here, just to say that much of our predictions, theoretical prediction, have been found correct experimentally. So once you get a good technique under your belt, like this Bogolubov-Digens method, or even more generally the inhomogeneous mean field theory, I mean, which goes beyond Bogolubov. I mean, you need not even have a Bogolubov channel, you need not even have superconductivity, but you can still work out, you can solve problems in a broad formalism like this, and that pays very rich dividend. It paid very rich dividend for me or for my group. Okay, so how, and then we have been looking into the vortices and stuff like that, disordered superconductor in a magnetic field, I mean, which is what we are very excited about in our recent research, but I don't have time to get into that. So now I have a quick question for Pretam. I mean, how am I doing with time? I mean, how much time we have? About 15 minutes or no?
Yeah, it's okay. We can.
15 minutes. Okay. So then I will change my gear. So this is something I would have liked to speak about because this is something we are doing now and very exciting results. But let's not get into that. So let me just quickly go into a second problem. And I'll be very, very brief in this case because so my objective was to sort of introduce you to technique, and then in the simplest possible manner, mostly for students, of course, as I mentioned, as I emphasize every time, that a technique which pays rich dividend for research. So this is one technique that I have talked about, and I thought of talking about second technique. I'll be brief here because I have little time. So let me still tell you what the problem is, and then what can one learn using that technique. So the physics problem, again, every technique is guided by some physics. So physics problem we are interested in is crystal of Coulomb particle and its melting. So the problem is the following. So now we are going to talk about not an effective attraction between electron, but the real long range Coulomb repulsion. So what happens, because in a electron gas, when you include in the electron gas, which is not free anymore, but you include the long range Coulomb interaction. So it turns out that people thought about it for a very long time. I mean, Wigner first talked about it. I mean, it is known. It goes by the name of Wigner crystal melting in hard condensed matter area. Quantum condensed matter, and this was predicted is 1934. It is such an old problem. I mean, and it is still very interesting problem, and people don't know everything about it yet. So that makes it very interesting. So what happens is that when you have an electron gas and you have a very low density of electron gas, you imagine what can happen. This repulsive electron will try to push each other as far as possible, and thereby lock them in a position such that they form a crystal. So that is given here. So I'm talking about the region where the electronic density is very small. So here you can resolve every electron. So you can think of this plot is like the probability of finding an electron. So that's very high and low. So there are very specific regions where electron can exist, and that's because electrons have locked themselves in. So every electron in this state, because of this long range Coulomb repulsion between them, so it's written here: Coulomb repulsion forces particles to stay as far away as possible from each other, and thereby localize them, forming a regular pattern or crystal. Something like a crystal. This is in a small region. This is not a crystal. Crystal is an infinite system, but you can think of it as a small part of a crystal, or a crystal of a small assembly of particle. In fact, we are going to talk only about assembly as we go along. It will be clear, but it will form like a crystal. But then, if you bring in kinetic energy, which is because of the overlap or like the hopping of electron that I was talking about in the previous topic. So that will try to delocalize electron. That will make electron move from one place to another. So now imagine starting with this kind of a crystal where electrons are staying far from each other, and thereby they are locked, and thereby there is no transport of electron. Now you start making the density higher and higher. Either you bring more electron, keeping the area of the system fixed, or you keep the number of electrons same and then squeeze the system. So then the chances of electron to hop out increases, because it can easily go to the next site, and thereby, I mean, they start moving around. I mean, so basically when you overlap, electronic wave function overlap more, and thereby electron delocalize more, taking advantage of the kinetic energy. And then the probability of finding electron becomes something like this, which is far more homogeneous distribution of electronic density. So this is what is called a Fermi liquid. So by tuning density, going to a large density of electron, starting from a low density of electron, as you go to a high density of electron, you transit into an electron liquid object, which is a metal, starting from a localized electron object, which is an insulator. And this is called Wigner crystal. And this transition from here to here, which is opposite to the arrow, is called a Wigner crystal melting. So now melting can happen starting with a crystal situation like this. Melting can happen either by thermal fluctuation. I'm waiting for the black patch to go away. Yeah, so now it is. So either it can be because of the kinetic energy that you have to supply, can be either of thermal nature, which is KBT, coming from equipartition theorem, and then underlying melting is called classical melting of Coulomb particle, or Coulomb crystal melting is how it is called. You can also have a quantum melting, which is where the temperature doesn't play any role. You just change the density. I mean, that's what I was talking about, and you can undergo a quantum melting. So you can have both classical and quantum melting, and I might come to quantum melting a little bit later. And this is a very, very relevant problem. People see such melting. So if you want to know what is the real picture of a real motivation for studying this kind of a melting, I mean, these are all experiment in dusty plasma at very low temperature. These are like the trajectory of an electron. So because there's a small size picture, you can't see it very well, and I'll show you quickly that you can form in a dusty plasma setup something like a crystal where electrons are all localized. Electrons are some charged particles. I mean, so charge carrier, I will say charged particle is all that one can talk about in this particular system. Dusty plasma, so it's a plasma dust essentially. So they jiggle around at their equilibrium position. That's like a crystal, and then as you can and you can tweak them by laser. I mean, you can increase the temperature by application of laser, the effective temperature in the system, and then with that high temperature they start moving around and they melt. I mean, this is something this people study in experiment. So to talk a little bit more about the melting, so let me tell these are the result from our group. So this is the melting I'm talking about, very similar to what I was showing you here in experiment. So this is a low temperature. So these are essentially a bunch of trajectory of a particular particle, charged particle, let's say electron for the moment. Okay, so these particles are localized. Even they're moving around, they're essentially jiggling about their equilibrium position here, just the way it happens in the solid. So it's just phonon vibration of a solid. Now, as you increase temperature, they move. I mean, the region of movement becomes larger, and this is from where people formulate a Lindemann criteria for melting. So this blob becomes larger, and not only that, there is now long range motion that starts to occur. And then at high temperature, every particle or every such electron moves around everywhere. The trajectory cannot be identified. Trajectory because of one particle cannot be identified to be staying around some equilibrium position like that, and you say that it has melted, right? So this melting in a circular confinement. So we are going to talk only about confined system, not really a bulk system. Confined in some way, and the way I will tell you mathematically how we do that, I will tell you, and experimentally they are very routinely studied confinement. So it can be done. I mean, for the moment, you just take that from me. So what we wanted to study is not the circular one. So circular one is like the most regular system or most clean system that you can have as a confined system in 2D. or circular confinement and the most symmetric one. Instead, we wanted to study the effect of disorder on that melting. How do you put in disorder? The way we do that is that we squeeze the confinement. We don't keep it as confinement like this. And this, by squeezing, we make an irregular confinement, so which looks like this amoeba shaped object. So even though it's an amoeba shaped object, there is a way to identify the one here. The system here is like a crystal, electronic crystal. But there is a difference of this crystal versus that crystal. I mean, this is not as good a crystal as it is here, but you can still, I mean, even in some kind of an irregular geometry, you can have something like a crystal. You can see that, I mean, in particular, what the one thing which identifies the crystal here, or I mean, some kind of a order here, is that every particle has 6 neighbor. And I'll tell you about that 6 coordinated neighborhoods. So about this, there are 6, 1, 2, 3, 4, 5, 6. So every particle you see, you will see that there is a 6 nearby. I mean, 6 neighbors it has. The nearest neighbor it has, which are essentially relative angle between one neighbor to the other one. Is line joining one neighbor to the next neighbor is about 60 degrees. So that remains more or less intact, as I will show in a moment. But the point is that here, starting with this crystal, I can again increase temperature and I can melt it. So when we started doing this, what was found as very interesting and impressive result is that here, even though it melts, very unlike the scenario here, whereas there is a clear progression, it turns out that the incipient melting, or melting, starts by creating regions where a lot of particles are very well mobile. They move a long distance like this, whereas many other particles are not moving at all. So this is what is termed in certain literature as dynamic heterogeneity. The dynamic signature of some particles are very different. I mean, they are very heterogeneous as the dynamics goes. Which is now clear probably to you. I mean, some particles are just jiggling around their equilibrium position, whereas others are making long distance moves. So that got us into it, and we tried to understand that. So what happens to this melting when you have irregularities and when you have disorder, and then what is the effect? So that's what we wanted to study. And the way we make this disorder is, as I said, squeezing the potential. So we squeeze the potential to introduce disorder. We keep 2 things in mind. So first of all, a single particle dynamics in the squeezed object will make a fully chaotic dynamics, just the way one expects classically. Whereas the motion here is completely integrable, right? Because it's a circular confinement, it's easy to see that the motion will be integrable. We choose a confinement which makes the motion completely chaotic. I mean, because that we think is a signature of disorder, one signature of disorder. Secondly, we kill by construction of this potential, which has a particular form, and we choose that because people have studied it earlier. Choose one where all symmetries are broken, because disorder does that. So complete chaotic motion as well as lack of any spatial symmetry makes it a disordered system as compared to this one. So we have studied these two as a comparison and tried to find out what new thing comes out of here in the melting process. So we use a variety of numerical technique, and because I have very little time, maybe just 2-3 minutes more, so I will just quickly tell one. I mean, not really doing a lot about it, but still try to do in 2 minutes introduction to Monte Carlo, classical Monte Carlo. That you start with some random initial configuration of all the particles, I mean, Coulomb interacting particles you want to work with, put it there. And that initial configuration, I mean, I call that a point in a configuration space R. R is a point in configuration space which is identified by position of all particles individually, R1, R2, all the way up to n particles. And then what I try to do is that we propose to move a particle from its initial position to a new position which is within a distance of delta by 2. So it can be done by some kind of a, so this is a random number, drawing random number, you can randomly move it up to a distance. And then once you propose a movement of a particle, then the new configuration, I mean, this configuration, initial configuration had some energy. Let's call that energy EO, old configuration energy. And you propose to move one particle, which will move to some other point. I mean, you can move more than one particle at a time. I mean, there is no problem with that conceptually, though technically it is done in in a particular manner. Again, because I'll have very little time, let me just talk about the conceptual part. So you propose it to move a particle, and once you move the particle or move a bunch of particles, then once you have moved them, you find a new energy, which is En. Right? If you have lowered the energy, that's fantastic, because you have done something better. So you accept the move, and then that becomes your new configuration. Now, if it turns out the opposite, that if the new configuration has a higher energy, so old is more favorable. So even then, you actually propose to move the particle. You don't say that if it increases energy, you will not move the particle at all. You move it, but with a very low probability. How low? So that will depend on the difference, the size of the difference, and because n is larger, so this difference is a positive number. So with a negative sign, it becomes a very small number. But with you move it with a very small probability. There is a reason why you want to move it with some small probability. That is because if you look into this configuration space, you will have, if you in the configuration space, you can write it as an energy. So you can write down this configuration space of all possible configuration and calculate their energy. And in some hypersurface, here it looking like a two-dimensional hypersurface, it will look like a very corrugated structure of energy. So locally, it might look something like that. I mean, there is ups and downs, hills and valleys and everything. And then, so your system at a particular configuration will stay at one point of this energy surface. And you'd like to go, because you want to talk about the equilibrium dynamics, or not even that. I mean, you are talking about equilibrium properties. You would like to go to the lowest energy configuration. So maybe you are stuck at some point, which is a local minima, but ultimately your goal is to actually trace the whole configuration space as much as possible, and thereby once you do that, you will generate more probability of being at the lowest energy state. But if you are stuck at one point, then you cannot scan the whole energy space or whole phase space. I mean, that's the way one says it. And to enable the system to overcome the barrier, you need to make this arrangement, and that's the triumph of Metropolis algorithm. I mean, so how to move your system in the configuration space such that you track the equilibrium, or you reach the equilibrium by jumping over the barrier. So that is implemented this way. And then you can pictorially describe that. I mean, so basically you say that you are essentially, I mean, Monte Carlo method represent dynamics of the system, but not in real space, but this configuration space. And it can be understood as a Markov chain process, which and then beyond that, I mean, these are all technicalities that I won't get into that. And then you can write a flowchart again. I mean, if you have to sit down and write a computer program to implement that, a flowchart will help. I will not describe that, because just Pretam, can you confirm me? I probably have exhausted my time, right?
Yeah, maybe 1 minute or 2 minutes.
1 minute.
I think you
okay.
can.
So that. Yeah, so thank you so much. So 1 minute is fine, because I don't want to continue forever. So I will just say this much, that what we found by implementing this method is that the dynamics in the system happens in very different way between circular and irregular system. So for example, in this irregular system, where this is the amoeba shaped, I mean, disordered system, So it is at a very low temperature. I mean, just take it from me. So what happens is that if you wait for certain times, I mean, so some small time here, t equals 100, so the particles essentially don't move. I mean, particles which are moving is given by its initial position, which is the dot, to the final position, which is joined by a stick. So you can see there is some small object which is like a stick, but it's a very small stick. So essentially particles don't move because they are all locked up in their solid position. However, because there is some still small but finite temperature, if you wait sufficiently long, some particle will, I mean, it may happen that one particle will jump out of a cage. By cage, I mean that, I mean, every particle is surrounded by six neighbors, and that those six neighbors forms a cage. So, and because of that cage, a particle cannot move very far. I mean, I mean, just force balance will make sure that this particle remains there at zero temperature. At finite temperature, it initially jiggles only a little bit, but then after sufficient time, it will gather some probability of making a long distance move. So make a big jump. So if it does, the jump will take it to take it out of its own cage and make it fall in a cage of a next particle, right? I mean, the next cage. So in that cage, now there will be two particles, so they will not like each other at all because they are Coulomb repelling. So again, one of them will jump, and this will keep continuing. So it will create an avalanche of process by which the particles will move around over a long distance in a long and tortuous path. So that's what is shown here. And even larger time, they will make larger path of their motion. And this is what causes this dynamic heterogeneity. So this is very different from a circular system. I mean, for irregular system, it can happen anywhere and there is no symmetry or nothing. Whereas in circular system, the symmetry dictates which way, if they at all make a long distance move, how they will do it. But here there is no such symmetry, and that makes the motion very different. And this motion that I just described in words, I mean, this we have identified and comprehended in all possible way. That's a signature of what is called a glassy dynamics. I mean, glass is just like window glass. I mean, that's a phase, dynamic phase, which is not an equilibrium phase according to many. So which is between solid and liquid. It's very rigid like solid, and it has a symmetry of a liquid. So many of the properties of this system, which is the Coulomb repelling particle in a disordered environment, is like a glass, whereas the one which is not disordered or not in a regular system, there is a very smaller element of glassiness. So glassiness increases by doing that, and that has a lot of consequences. So all that can be understood, and we have done that in great details, and I didn't plan to even talk about that. So learning a simple Monte Carlo, classical Monte Carlo, can teach you many things which are interesting. And then you can take it further to build in quantum fluctuation, but that will be a lot more. And then you go into developing something even more sophisticated numerical methods, which we have been doing. I mean, path integral Monte Carlo, variation Monte Carlo, diffusion Monte Carlo, these are all different type of quantum Monte Carlos. And you start from classical Monte Carlo and then slowly develop into the other one, and you keep learning more things. So I wouldn't say too much more, but before I end, I'll just acknowledge my collaborators. Most of them are my students. I mean, Duti was my first student who worked on problems like this, who went to Harvard for her postdoc, but then now she has gone to industry. Then Bishwarup Ash, who is a postdoc now, is Weizmann. Demal Chakravarti, Anurag. I mean, Demal is in Uppsala now. Anurag Banerjee in Saclay in France, and Anusri Datta, who was supposed to start this summer in Spain but is delayed because of COVID situation. So they are my main working force. They are my PhD students, and then we have some current PhD students, and then there are other students who are like undergraduate students. I learned a lot working with all of them. And then I also benefited collaborating with senior colleagues like Chandan Das Gupta at IIS Bangalore, Jaydev Chakravarti at SN Bose Center, Kolkata, Rajdeep Sen Sarma and Pratap Rai Chaudhary from TIFR, and Nandini Trivedi from Ohio State University. So big team, and I benefited a lot by interacting with them. So I will stop here. I think I have exceeded the time enormously. I'm so sorry about it.
It's okay, sir. Thank you, sir, for your wonderful session. So if you allow, sir, we can start our discussion session. We have got some question in. So the first question is BCS theory applicable to high temperature oxide superconductor?
No. So this is a very good question. Okay, I remember this question, but something we did last time so that I could also see the question. Is this possible here?
Okay, yeah.
What do I have to do?
You should stop sharing.
Okay, so stop screen. Okay. So right. So BCS theory, high temperature oxide superconductor. The answer is no. The main reason the answer is no is the following: that people believe the answer is no, because I said, when I talked about, I basically gave the idea of BCS theory. I said that they are electron effective interaction mediated by phonon. So now it turns out for high temperature. So now, because if you know the material, you can find out what is the coupling strength for this electron phonon interaction, and then what kind of coupling strength you will expect for, what is required for uh, uh, basically ramping up the TC to the value which is found in copper oxide superconductors. So they don't match. So that's the reason why people believe that the electron phonon interaction is not the reason why you generate an effective electron interaction. So that was crucial part of BCS theory. So that is not, from that perspective, the copper oxide high temperature copper oxide superconductors are not BCS theory. But BCS means various things to various people. So the nature, the origin of the effective electron interaction has to be something different from this effective electron interaction mediated by phonon for high temperature superconductor. But you can set up the and what exactly is the origin of the interaction, effective attraction in these superconductors is not known yet. People have very suggestions, but none of them appear to be really the answer compared to any other, and that's why this problem is an unsolved problem so far. This is what people don't know. But if you want to say that, okay, no, I will not call that a BCS theory. The origin of interaction, I don't care. But the fact that I will do a mean field theory is what makes a BCS theory. That you can do. Then you can develop a mean field description. So the mean field, excuse me, mean field description actually doesn't work very well, because it turns out, unlike the metallic BCS superconductor, or metallic superconductor where BCS theory works, in this superconductor, in the high temperature superconductor, the electronic interaction strength is very high, very large. They're strongly correlated superconductor. So there is some difficulty in applying the straightforward mean field theory that I was sort of motivating for developing the Bogolubov-Digens technique. But you can make way. You can work around that. There are ways to take care of this strong correlation within that kind of a mean field setting. So you can. Sometimes people say this is there is a technical term. These are also, they're not BCS superconductor in the sense that I didn't talk about it. The wave, the order parameter in momentum space has certain symmetry. So BCS theory demands that the superconductor has order parameter which are isotropic. So in high temperature oxide superconductors, they are anisotropic order parameter in K space. So there are many ways you can say BCS versus otherwise. So, but people normally believe that this interaction, the origin of interaction, what identifies, what made BCS theory successful for metallic superconductor, that does not work. But you can work out work out the anisotropic order parameter mean field theory for high temperature superconductor, keeping track of strong correlation, strong electronic correlation. So to that level, you can say that you can work with a BCS theory for such superconductor. So depends on what exactly you want to be in BCS. What identifies BCS theory for you? It is anisotropic order parameter. It is strongly correlated. Those are against the idea of metallic BCS superconductor. But mean field theory, you can still formulate. Yeah. So that's the answer I will give. But for interaction origin, the origin of interaction, no, it is not like BCS. Yeah, does that satisfy?
Thank you, sir. We have another.
Okay.
Yeah, we have another question. So, how pressure can change the superconductivity? Is it possible to discover a superconductor in room temperature and pressure?
So pressure has a very important tuning parameter on superconductor, and sometimes pressure can create superconductivity from something which is an insulator, and then application of higher pressure can destroy superconductivity. So how pressure changes superconductivity is a more detailed question. If you I mean experiment I mean This is mainly the experimental finding, and the answer is that it can do both, and how it does both is a little bit involved. But let me tell you that there are superconductors in superconductivity. People find what are called transition metal dichalcogenides, which this is just one example I'm telling you about. There are many other example pressure induced superconductivity. So in this transition metal dichalcogenides, they're believed to be insulated. There's a charge density wave insulator. It's a particular kind of insulator, but let's just consider them to be insulated. If you take them at normal pressure or atmospheric pressure, or maybe a low pressure, starting from there, you increase pressure, it will first destroy the charge density wave or the insulating behavior, and thereby it will nucleate superconductivity. So pressure can do that, but if you keep on increasing pressure, the superconductivity will get destroyed again. So it's not something which is just one answer. The other way of looking into it, simple theoretical way of thinking about the effect of pressure on superconductor. So we talked about this hopping, like T, hopping amplitude, the probability of hopping from one side to the another. So in an electron, when you apply pressure, of course, you can imagine that the lattice spacing becomes smaller. So that will change the hopping probability of an electron from one lattice site to the nearby lattice site, right? So that is one way in a calculation you can take care of the. This is one way you can think of incorporating pressure. So now the second part of the question is, is it possible to discover superconductor in room temperature and pressure? And that's the question that many people are too busy with, I think, in recent times. And then there are in halide materials, it has been found in recent times. There is a lot of excitement about it. I wouldn't get to that. It is So there. That is. Basically, so in nutshell, the statement is that people have found a way to find a superconductor or a material that superconducts at room temperature or nearly room temperature. Room temperature is different between Alaska, for example, right? I will say that it is at a temperature which is the ambient temperature of certain part of the world. People have discovered material which will superconduct. Only thing is, they will superconductor at a very, very high pressure. Very, very high pressure. So that pressure is hard to create, but people believe that can be mimicked by some kind of a chemical pressure. So people are very close to that. I would say that it will be it will be possible to have a clear answer to this question in near future. Yeah. What is the
Thank you.
zero resistance? Okay. So, what is the explanation of BCS theory for the zero resistance of superconductor? Okay. Uh, so uh, I mean, so uh, so it is basically, as I was telling, that Cooper pairs, I mean, that you form by binding to electrons, they form a boson, and that changes much of the properties of electrons. So that leads to very important outcome, including this zero resistance. I mean, it is I don't know whether I'll be uh, okay. So there are many things I can say physically. I mean, so first of all, this is a standard calculation that one can do, and one does. I mean, when one learns BCS theory, that within the premises of BCS theory, within the formalism, one can show that by calculation. That is hard for me to do right now. I will certainly, if you write to me, I will sort of guide you how to do that. Physically, I think it is one way to think of it is that because this is not an exact answer, but one way to think of it is that because there is an energy gap. I mean, so it is like the ground state is protected by from external perturbation. I mean, that's the reason why there is an energy gap, and then once you cannot really probe the ground state because of the existence of a gap, so everything start looking like perfect because you can't disturb the system. So that's one very broad way of saying that the resistance, I mean, basically, you can't disturb the system. I mean, the resistance will go to zero. But it has to do more with the fact that it forms Cooper pair, and then it becomes bosonic, and then many of the behavior of because it condense, and that's the reason. Yeah, maybe I'll if you write me a mail, I will guide you, or I will suggest you some of the literature or some calculation where one can see that more directly.
Thank you, sir. We
Yeah.
have another question. So, is there any experimental evidence of quantum spin liquid?
Okay. So so quantum spin liquid I didn't speak about. Any evidence? I think there are some evidences. I mean, some. I'm trying to remind myself the name. Hyversmith. I'm forgetting the name of this salt. I mean, which shows some a class of salt which shows the property of spin liquid. So the thing is, the answer is yes. I mean, that there are some evidence, but only very few. So yeah, and people are very so it is a state which exists. I mean, which can exist theoretically. It's a state which is very different from many others and can still exist. So sorry, to switch it off. That's true. So spin liquid, there are some material, and we have very good experimentalist in India, in Mohali, IISER Mohali, who is working on constructing or fabricating spin liquid material. There is a lot of research, and the research is there everywhere around the world, and so there is a lot more to be done on experimental front as well as in theory for spin liquid. What are the
Thank you, sir.
most
This
important
yeah, this
simulation
means a lot.
techniques? Yeah. Right. So, yeah. So this is, I mean, this is little hard to answer. I mean, it is little hard to qualify because most important is unclear. So I would say it's best to think in the following manner, that you. I mean, So you will pick up a simulation not because it's the best or it's the most important, because it solves a particular problem. So if you have a problem which is important problem to solve, I mean physical problem, phenomenologically it is an important problem, then anything that solves the problem is an important thing. So that's the way I would like to think. So there are many techniques, many numerical techniques which have helped understanding various phenomena. A class of such techniques are called quantum Monte Carlo for quantum systems. I mean quantum Monte Carlo, and then for classical system, their equivalent classical part is classical Monte Carlo, which I was describing. And then there are many different quantum Monte Carlo, because the algorithm which you use to do the particular job of this simulation is different for different Monte Carlo. So that, and I think somebody told me that there are actually 24 different quantum Monte Carlo techniques, but there is a lot of similarity between them. So Monte Carlo, quantum Monte Carlo is a class of technique which had been very, very important, but at the same time there are, I mean, important in understanding the role of strong correlation in particular. But then there are other techniques, other set of calculations which are often called the first principle calculation, band structure calculation, like density functional theory, which are techniques which are conceptually not very difficult, and hence and also numerically it's not very demanding. I mean, it's not very expensive numerical calculation given the kind of answer they come up with. So the given that very important answer they come up with. So many times if you are designing some material, these techniques are the techniques method of choice. I mean, DFT, density functional theory calculations, and then people are trying to improve those calculations in various ways by building in strong correlation. So that's a separate line of calculation. So they are important for certain purpose, particularly by matching with experiment, or guiding the development, designing of devices, etc. And then there are other techniques, DMRG, density matrix normalization groups, and other stuff, I mean, which are, so all these are very important techniques and numerical techniques, good for certain target. I mean, so for your target, whatever works is a good technique, I would say.
Thank you, sir, for your wonderful presentation and exciting discussion, sir. So, as there is no question, we can conclude our session, sir. So, we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. You have gave 2 lectures.
Yeah, thank you so much for.
Yeah, so our students have learned a lot of things about condensed matter physics. So, the main aim of our program is to motivate and encourage our students. I think by your lectures have motivated in this condensed matter physics, and hopefully in near future we will arrange another webinar with you if you are free.
Sure. Yeah.
Thanks again, sir.
I mean, I really enjoyed interacting with you and your students and everybody. So it was a great fun. Thank you for having me.
It's my honor and pleasure, sir, to host you in my international physics. Thanks again. See you and good night, sir.
Thank you. Good night.